So let's look at situations where the Clemmensen reduction and the Wolff-Kishner reduction might also react with something besides benzylic aldehydes or ketones. All right. So let's do Clemmensen first. So Clemmensen reduction involves the reducing of the aldehydes or ketones, and that uses zinc and HCl. Right? So which makes this special. The problem is, do we know other reactions or other functional groups that react with HCl? What's something that reacts with HCl? Alkenes, right? Alkenes are alkynes. So let's say I put an alkene out here, right? Is that alkene going to react with HCl? Yeah. Yes, right? What's it going to? So I'm going to still do, right, that benzylic reduction of the ketone, right? I'm still going to do that, but I'm also going to, right, add the chlorine to the more substituted carbon of the double bond. Right? So Clemmensen reductions in this case might not be the best choice. Right? So in this case, instead of using Clemmensen, you might want to use if I used H2 palladium on carbon, what would happen? That would reduce the double bond, right? So that wouldn't be good either. So what would be the best choice here? Probably the Wolff-Kishner reagents, right? So I would use Wolff-Kishner here instead. Right? So that's when, those are the times when there's an alkene around. You gotta be careful about using H2 palladium on carbon. Alkynes, same way, yep. Alkynes will act with HCl as well. So that's the Clemmensen reduction. So let's look at a Wolff-Kishner situation where the Wolff-Kishner won't work. So this, or how, or where else it could react. We just actually learned this. So let's say, again, we have a ketone, a benzylic ketone, and now we have a bromide here, right? In the Wolff-Kishner, right, we use H2NNH2 and OH minus. So again, it's going to reduce the benzylic aldehyde or ketone, right? So that's still going to happen, always will. But the problem is, what else could a strong base do with this bromine that we learned? That it could either substitute it, and so switch. So we could get, right, instead of having a Br there, we could have an OH there now. What other product could we make?
Just without the Br.
So so that's a substitution, right? I substituted here. What else did we learn away? Why else did we put bromines in that benzylic position? What else did we do with them? We substituted them. We also did what with them? Turned them into what? Eliminate them, right? Turn them into double bonds, right? So you'd get a mixture of two products. You'd get it so the bromine was substituted with the OH minus, and you'd also get it where the OH minus acted like a base, took the H right here, and formed an alkene. So look back at your slides from Monday. We talked about, right, if you have a bromine in that benzoic position, right, you can either substitute it with a nucleophile, or, right, you can eliminate it and get an alkene. Right, so this would be a case where, right, if I have a bromine sitting out here in the benzoic position, I wouldn't want to use Wolff-Kishner then, right? Because that would do another reaction. Could I use the H2 palladium on carbon in this case? Mm-hmm. Sure. Could I use the Clemmensen? Mm-hmm. Yeah. Right. So it'd be okay there.
Like P, because of like the reaction and like the study question, like we use copper versus
Palladium. Yeah. So basically for organometallics, so like this on the study guide, it asks us, what does it say exactly?
Can you predict the product?
Yeah, so I asked you, can you predict the product with copper or palladium metal, right? Same idea basically for both of these. Remember, metals are essentially a place for two things to come together, right? So in one of these cases, let's say if something is bonded to palladium, right, and something else has a bromide, right? So essentially a metal creates a place where normally you couldn't create bonds. A metal allows you to create bonds. But we know something about metals are not very electronegative, right? So whatever's attached to the metal, the carbon there is going to be electron rich, right? So that's going to be the nucleophile, right? Right. Same things hold true, right? Remember we talked. Every reaction still needs a nucleophile and an electrophile. And metals are just helping facilitate more unusual pairings, essentially, right? So if something's bonded to a metal, that makes the carbon a nucleophile, which is nice. And then if a carbon's bonded to a bromine, that makes this carbon an electrophile, right? And there's a whole process of how this works. But essentially what happens is this metal allows these two things to come together and form a new carbon-carbon bond.
And bromine
And then bromine and palladium are kind of off on their own, doing their own thing.
and at the moment, that's all we need to know.
That's all you need to know. I want you to be able to identify the thing that's bonded to the metal is the nucleophile. And then if the other thing is bonded to more electronegative atom, that carbon is going to be the electrophile. That's what I'm looking for. Right? And the same thing if this palladium was copper, same idea. Magnesium, lithium, same idea. Yep. So one thing I would say about the magnesium one, the example I showed in both classes, was it can behave more like, right, I showed you how to make, so like a Grignard. I said you could have this, right, you could have bromobenzene, which right now this carbon right here is delta plus, right, it's an electrophile. But the neat thing you could do is if you add in magnesium, now that carbon that was delta plus is now what? Now it's delta minus. So you've changed its reactivity, right? From being delta plus to being minus. Right? You've turned an electrophile here, you added the metal, and then it became a nucleophile. Right? See how that's a nice way to do change your activity? And then essentially, since it's just a nucleophile, what if I had in the mixture, then I added in something like this? Right? Now here we have our nucleophile. Here we have a good electrophile, right? What if these electrons came, attacked, and just substitute out the bromine for that whole phenyl ring? So our end product's going to be if I number this carbon 1 and this one 2, here's 1 and here's 2. And then plus Br minus with the magnesium bromide. No, this is special with magnesium. Magnesium or lithium does these kind of substitutions. But the same idea holds true, right? If you're bonded to the metal, right, the carbon's going to be the nucleophile, have electron density. So, explaining essentially pKa's based on electron donating and electron withdrawing groups, right? How do we understand that, how that affects that? So let's look at two examples, or we'll give you three, I guess. One with NH2. There's an OH. I'll do another one with NH2 in the meta position. And then, it's not like this. So it's similar to a homework problem. There's one of the homework problems had nitrile. This is going to be a little different. So NH2. So first thing we got to ask ourselves, what are we talking? When we say acid base, what are we talking about here? We're talking about the most polar bond to hydrogen, right? That's the acid. So these are all acids. So what bond are we talking about here? Which bond? The OH bond, right? We're talking about the OH bond for all of these, right? So one way of looking at this is now we got to look at the substituents, right? So the only substituent we have here is NH2. Is that an electron donating, electron withdrawing substituent? It's a donating substituent. Good. One of these cases there is no substituent. In the other case it's meta, and the other one's para. So there must be something different about the resonance structures that's going to influence this, right? anecdotally, if I push electrons towards the ring here, what's that going to do to this bond? Make it stronger or weaker? If I push electrons toward it, it's not going to make it weaker, is it? Yeah. So electron donating groups usually increase or decrease pK. Usually increase the pK, right? So I know that this should probably be my best acid, just based on that, right? But I got to figure out between these two. So the best way to do that is to look at the resonance structures of the conjugate bases. So let's pretend these things reacted. We'd end up with O minus, right? So now it's a matter of moving these electrons around the ring, right? Draw on these resonance structures and see if any one is good or bad or otherwise. Oops. Keep moving the electrons around. Got some resonance structures drawn. Is there one of these resonance structures that you think looks particularly maybe not so awesome?
The first one.
So, what's wrong with the first one?
The oxygen having the minus charge.
So is that good or bad? Is oxygen electronegative? So would you rather who would you rather have it? Yeah, so you'd rather have the opposite, right? Have the oxygen negative charge. Some people say the third one. What's wrong with the third one? Electron density. Electron density. That's not good, right? So that's not going to be a very stable product, right? If it's not a very stable product, it's probably not going to be a very good acid, right? So this is probably really bad, right? But what about this one? How do we compare? Right, so we've done the para one. Now let's do the meta one. How do we compare those two? All right, so let's draw out the meta one. Maybe. Bear with me. All right. Bring the electrons down. First we gotta draw the meta position. My bad. Where are you guys on that one? Come on.
Quick definition question, are these sigma complexes?
No, these are not sigma. These are not sigma complexes. These are sigma complexes are only in electrophilic aromatic substitutions. This is not an electrophilic aromatic substitution. This is an acid-base reaction. So I need to redraw this. It's here. It's in the meta position. Take my word for it. Move these electrons there. What you'll find is there going to be a structure where the electrons are right next to the NH2? No. And that's the whole point, right? There is no structure where it's right there. So what's worse, right? So this is still donating electron density, but it's not as bad. It doesn't have a conjugate base where it's really bad like this. So if you rank these, right, according to acidity, you would say this one was the most acidic, then this one, and then this one. Lowest pK, highest pK.
And NH2 is electron dense because it has that lone pair, or why?
That lone pair, yep, it's electron donating because it has that lone pair, absolutely. That's right.
So which one's lowest pK?
Lowest pK is the one with the lowest pK is just the phenol by itself, without any groups on it. Because electron donating groups, no matter where they're at, is going to make it less acidic.
So the least stable is the most basic?
The least stable is the least acidic. Right, we're talking about acids, yep. So yeah, the least stable is also the most basic. But kind of a different question. Let's take a look at electron withdrawing groups. So if I put what if I even did something like this? Put a carboxylic acid and said, what if I have a nitrile here? Put the nitrile, right? So one case the nitrile's para, another case the nitrile's meta. Which one of those is going to be, right, have a lower pKa? So same exercise again. You know they're both nitrile groups an electron donor, electron withdrawer. Withdrawer. So you know it's going to decrease the pKa, but you can't tell without drawing resonance structures which one's going to have the greater effect, the meta or the para. So let's draw the resonance structures. Right. So this is a little different, right? Can I draw resonance structures into the ring this way? It's going to be a little harder, right? So what kind of resonance structures can I draw, though? Maybe I don't like my example as much anymore. We'll see. Let's draw them out. Let's see, right? Let's see. So what if I drew electrons going here, right? Just breaking that pi bond. Okay. Keep thinking. There?
So electron donation increases the acid strength.
Decreases the acid strength.
Increases. Okay.
Right, electrons go there. Electrons go there. Okay. So you have 4 resonance structures here. Any one particularly that you like better than others? There should be one. That's a good one. First one's probably the best, right? But which one gives us information about how the nitrile is affecting this? So the first one's probably the best because it's the least amount of charge. Right? But which one of these tells us how the nitrile can affect this? So the nitrile is electron donor or withdrawer? Withdrawer. So it wants to be next to a positive or negative charge. So which one of the 3, 1, 2, 3, is the nitrile next to a negative charge? 2. Everybody see that? See there's the negative charge, there's the nitrile? Right? Yeah, 3, sure. This one. Right? The carbon here is delta plus, right? Because it's bonded to nitrile. There's nitrogen. So having the negative charge next to this is good. Right? That makes this complex more stable. Right? Now, if this was in the meta, do you ever see in any of these resonance structures, do you see a negative charge in the meta position ever? No. So if the nitrile is in the meta position, does it get this good resonance structure? No. Right? So which one's more acidic? Para or meta?
Para.
Para is more acidic because it has a more stable resonance structure.
But the last one we had like a minus near a nitrogen, which was bad.
Right. So you want to have, if you have an electron withdrawing group like a nitrile, you want a negative charge near it. Right? Opposites attract. Right? If you have an electron donating group, you want it to be next to a plus charge, not a minus charge. Opposites attract. So to re-clarify, para versus meta. Para is more acidic because its products, right, these conjugate bases, one of these has a resonance structure where the negative charge is next to the electron withdrawing nitrile, which makes it more stable. Whereas the meta version would never have the negative charge there, so it can't have that extra stability. Right? They're both going to decrease the pKa, but when it's in the para position, it has a greater effect. Okay, so let's look at a Friedel-Crafts alkylation. And this is the problem with this one, unlike all the other ones, carbocations. That means rearrangements. So, we'll just take a basic benzene ring. We're going to have it react with this alkyl group. We need to use AlCl3 as a catalyst. Right? So the first step in all these 5 ways, right? Halogenations, nitrations, sulfonations, Friedel-Crafts alkylations, Friedel-Crafts acylations was we had to generate the electrophile first. Right? So that's the first thing you need to do. So generate the electrophile. Again, we talked about metals being delta plus, right? Aluminum is a metal. So the electrons from chlorine attack the aluminum. So that gives us AlCl3 right? Now the chlorine lost electrons, so it has a plus charge. And aluminum got electrons, so it has a negative charge. And you can imagine aluminum is not happy with a negative charge, so this bond right here is going to break. And then we're going to form a carbocation. And the aluminum still has a negative charge. Once you form a carbocation, right, those will back to the rules we knew before, right, where if you can rearrange to a more stable carbocation, you will, right? And you can either do hydride shifts or methyl shifts, right? Move alkyl groups or hydrogen groups. So right now we have a secondary carbocation. Can we make that more stable in this case?
Yes.
Right, so what would we have to move? Hold on a second. What have I not done? 1, 2, 3, 4, 5, 6. Okay. So carbon 2 has the plus charge. How am I going to make a more stable carbocation? What am I going to do? A methyl shift. Okay, what does that mean? Which one? Which methyl should I move? 4, 5, or 6. One of them, right? Let's do 4. So that means the 2 electrons here are literally taking that CH3 up here with them. And so now carbon 2 is bonded to carbon 4, right? And carbon 3 now has the plus charge, right? So 1's here, 2, and now 4 is bonded to 2. 3 has the plus charge, 5, and 6, right? So what kind of carbocation is that? So can I make it more stable? Is there any like lone pairs I can stabilize this with? Nope. So it seems like this is the best it can get, right? So once I got the carbocation set, I'm done with that. So now I've made my electrophile. Now I need it to react with my benzene ring, the nucleophile, right? Don't forget that. What was the nucleophile? What's the electrophile in these reactions? Benzene ring is always the nucleophile. All right. So let's see. I'll just draw in the benzene ring over here. Pi bond attacks. Should I number the benzene ring? Yeah, you should always number the benzene ring. The answer is always yes. To numbering your carbons. Right? So the pi bond between 8 and 9 attacked. Where do you guys want? Which carbon do you want to get the bond? 8 or 9? 8 wins. Because it doesn't matter, right? In this case, there's no substituents. If there were substituents on there, would it matter?
Yes.
Oh yeah, good. So let's number these carbons. So there's 8, 7, 12, 11, 10, and 9. 9 has a plus charge. So this is carbon 3 here, right? What else was carbon 3 bonded to? Carbon 6. Okay, that's 6 there. It's bonded to what else? 5. Okay, that's 5 there. What else is 3 bonded to? 2. Okay. There's 2. What else was 2 bonded to? 4 and 1. All right, so see how I did that? All right, that way you don't lose track of things. All right, number your carbons. Now at this point, end of the day, we need to re-aromatize. Now at this point is where you can draw sigma complexes of these. Okay? But if we're just going to do it quick and dirty, at the end of the day, we're substituting this whole group. Right? This whole group is substituting an H. So then we use our AlCl3 because we need to regenerate the catalyst. Right? Remember, it's a catalyst. And remember that even though the aluminum has a negative charge, where's the electron density at? It's on the chlorines. So these electrons take that H. Electrons go down. And we end up forming, re-aromatizing, reforming the benzene ring. Making HCl. And then regenerating AlCl3. You can number the carbons out. There's 8, 7, 12, 11, 10, 9, 6, 5, 3, 2, 1, and 4. For a diazonium salt, oops. Right, that's when you get right, that's when you have the N2, like the nitrogen gas, like a good leaving group. And remember I told you guys 7 ways to substitute off that. Right? So you can replace that with a chlorine, an iodine, a bromine,
Hydrogen.
a hydrogen, H minus, OH minus, a cyanide. Right? So I told you 7 ways you can do that. So that's a nice way to turn, right? Because where did the diazonium salt come from? What was it before? One step back, it's what? It's an amine. It's like an aniline. And one step back from that is an NO2. It's a nitro group. So again, it's a nice way of thinking about, kind of thinking about how to shift chemistry around, right? An NO2 group is a donator withdrawer. It's like the ultimate withdrawer, right? But then an NH2 is a donator withdrawer. NH2 is a donator, right? So you've kind of switched, right? NO2s probably won't react at all, but you can change it to an NH2 so it reacts, and then it's going to direct ortho and para. And then even in a further step, you can take an NH2 and just change it to something else, right? So it's a way to control some of that reactivity, right? And change things around. So it's a nice way to do that. It makes sense?
And the only way to change it is the H2 and
Yeah, so let's
something like
so let's go back. So this is working backwards. So what reagents would I use to take an NO2 group and reduce it to NH2? What do I use?
H2 palladium.
H2, PDC. And to turn NH2 into N2 plus, what I do is NaNaNO2, right? And then there's the 7 different ways to substitute it off, right? If I asked you guys, what is this? Is this a donor or withdrawer?
Withdraw.
Withdrawer. So it's going to direct
Meta.
meta. Good. Okay, so this is going to be a purposely challenging problem, right? Using a lot of concepts we used in this chapter, then stuff from last semester as well. First thing you're going to be able to do when you look at this, you want to work backwards. So, if you look at this, starting from plain benzene. This has to start from plain benzene. We're going to start from plain benzene. So let me draw plain old benzene. We know the sulfonyl group here, we want to put that on probably last, right? Because that's a really strong deactivator, right? So I don't want to put that on first. So that's going to direct meta anyways. And these things are para to each other. First thing you need to ask yourself, so I'm not going to probably put that on, I could probably put that on last, right? So let's say I do that, right? So let's take off that as maybe an easy first step. So now we have this, right? How do we go one step back from this? So what do we have here? What kind of functional group do we have here? We have a what? An OH, which is a alcohol. What kind of alcohol do we have? It's a, you're thinking right. It's a primary alcohol, right? How many ways do you guys know how to make primary alcohols? One from last semester. And what was the starting material you used to make a primary alcohol? It's basically, you have two choices really, guys, right? You did a whole chapter on alkynes and you did a whole chapter on alkenes. So it's either going to be an alkene or an alkyne. How about an alkene? Good. Right? We can make primary alcohols from alkenes.
Are you saying that substituent will be para-directing?
Yep.
Okay.
Right? Because this is an electron. This is a electron donator, right?
Yeah.
So direct either ortho or para. Okay. So we can make primary alcohols from alkenes. We'll worry about the reagents later. How can we make alkenes? You guys know one way to make alkenes. How would you make alkenes? What do the alkenes have to come from? It could. It could come from an alkyne. You could reduce an alkyne to an alkene. Or it could have came from having the bromine right here, right? That's the elimination to make an alkene, right? We talked about having the bromine in the benzoic position. You can either substitute it or you can eliminate it.
Would you rather us do an alkene if it was more?
We could go, the alkyne one's going to be a little more tricky to do, but you could do it. I could show you how to do that too. Actually, I'd be pretty creative. I could show you how to do that. We'll do that in a second. All right? So from here, where did this come from? I don't know. What did it come from? Just a 2-carbon chain. And this could come benzene. Right? Because a 2-carbon chain, you can't really rearrange, right? So you can still do Friedel-Crafts alkylation. You can still do acylation too. Just add one more step. Still fine. So let's go the forward way now. All right. So now if I'm going to do this, if I want to add a 2-carbon piece, what kind of reaction am I going to do? Friedel-Crafts alkylation. So I need to add 1 2-carbon. So I need to have a CH3, CH2, Cl, and I need the AlCl3. Right, that adds that. This would be carbon 2, and that would be 1. If I want to brominate the benzoic position, what do I use? Br2 in light, HV. You just say light. Good. Light. If I wanted to eliminate the Br, I use a bulky base. You can say bulky base. Big base.
Can we say that on the test?
Please do. Draw a picture.
Wait, what would be a bulky base?
Big base.
A O- with a big terp butyl on it. So, once you use your bulky base, right? Once you use your bulky base, what reagents do we use to make a primary alcohol from an alkene? BH3. BH3OH minus, right? I knew it. And then what reagents do we use to add the SO3H? We use two H2SO4s. Good.